All right, welcome, PreCalc. We're going to get started here on section 11.1 and 11.2 today. So you guys should have your textbooks out. Section 11.1 starts on page 432, and we're going to briefly talk about 11.1 because it kind of leads into the more important part of 11.2 and so on. So what we're going to do is we're going to kind of go over the textbook. I'm going to briefly sort of run through it and kind of create some handwritten notes. I think we're going to start doing that now. So if you want to make sure you have your textbook so you can follow along and a notebook so that you can be taking your notes, I'll try and keep them brief, but point out the most important things for you, okay? So let's take a look. 11.1, what we're going to be talking about is we're going to be talking about power functions. And it's really brief. We're not going to go too far into this section. So a power function, here's how I like to talk about a power function. So this is going to be 11 point, oops, let's get rid of that. 11.1, and we're talking about power functions. And what a power function is I like to consider it one single term. So a power function is one single term. One term where, let me just give you the form. So it's one term in the form f of x equals kx to the p. Okay, so k and p are constant values. Those are just really any numbers. But the important part of this form is that the variable is going to be your base. Okay, so the variable is the base. So anything like an exponential function would not be considered a power function because the variable is in the exponent for exponential functions. For power functions, the variable has to be in the base. It is the base, okay? And it's one single term, right? So there's no other things other than this, right? It's just pretty much three pieces to it. You can have a coefficient, right? The k value, and then you have your variable as the base, and then you have an exponent, which would be the p value here, okay? And so that's essentially a power function. Now, what we're going to be talking about in terms of power functions is we're going to be talking about the end behavior of certain types of power functions. I'm not going to get into all of them because we're just going to go over the ones we need. So what we're going to talk about is the end behavior of all right. That's an E. There we go. End behavior of power functions with positive integer exponents. Okay, so what does this mean about this form kx to the p? That means that the p value, the exponent, is got to be a positive integer. Okay, so example here. Okay, we can have let's talk about two things actually. Let me change that actually. So here's what we're going to be talking about. We're going to be talking about when the exponent is an even number and remember we're talking about positive values here, and we'll be talking about odd exponents. Okay, so if we have a power function that has an even positive exponent, then we're talking about the end behavior in the long run. What that's going to look like in the long run, all power functions with even exponents will resemble x squared. So in the long run, all even exponent power functions look like x squared. Okay, and that's going to be important to remember because we know what x squared looks like. It's just a regular parabola. Odd exponents, well, all of those are going to look like x cubed, again, in the long run. They're all the same as x cubed. So what do we mean by this? We're talking about end behavior. So remember, if we're talking about end behavior, we can talk about the limits. The limits as x approaches infinity, right? As x gets really, really big, what happens to the function? So, for example, if we have an even, right? So find, let's say, find the end behavior of f of x equals, let's do x to the 4, right? Even exponent. This would work for any power function with an exponent of an even number. So let's look back at this graph, right? What is this going to look like in the long run? It's going to look like this. And so what is the limit as x approaches infinity of x to the 4? So as x approaches infinity, so as we go to the right, what happens to this graph? Well, the y values go up to infinity. So the limit as x approaches infinity of x to the 4 is equal to infinity. And the limit as x approaches negative infinity of x to the 4, well, as we go to the left, right, as x approaches negative infinity, what happens to this graph? What happens to the function? It goes to positive infinity still. So that limit is equal to infinity as well. Okay? Now, let's take a look at an example of an odd end behavior. So what's the end behavior of, let's say, f of x equals x to the 7? Okay, well, that's going to look like this. I like to just sketch those out just so that I have them there. So the limit as x approaches infinity of x to the 7 is equal to, well, as we go to the right, what happens to the function? It goes to infinity. And the limit as x approaches negative infinity of x to the 7, as we go to the left, the function goes to negative infinity, right? It goes down in those negative values. Okay, so there's even and odd exponents, power functions, and their end behavior. Now, those aren't the only two cases really, because what can happen is, let's take a look at something else. So let's take a look at this example. let's find the end behavior of f of x equals, let's do negative 6x to the 5. Okay. Negative 6x to the 5. This is a power function, right? So there's three pieces, a coefficient, x is your base, 5 is your exponent. Because 5 is the exponent, it's an odd exponent. It's going to resemble x cubed. But here's the thing we have to remember. If we think back to transformations, we have a negative coefficient, right? So a negative coefficient, what does that mean about the graph of the function? Thinking back to transformations. Well, what that's going to mean is that it's going to be a reflection over the x-axis, right? So if we have, let me go back up here. We have this x cubed graph, right? Then we're now going to reflect it over the x-axis. And so what this is going to look like, and this is why I kind of just sketch these all the time. So I have a negative coefficient and I have an odd, so it's going to look like x cubed but reflected over the x-axis. So it's going to look like something like that. Right? And so now I can just kind of graphically identify the limits, the end behavior. The limit as x approaches infinity of negative 6x to the 5 equals, as I go to the right, what happens to the function? It's going down to negative infinity, and the limit as x approaches negative infinity of negative 6x to the 5 is equal to, as I go to the left on this function, this goes up to positive infinity. Okay. So that's essentially all we're talking about in terms of power functions. Okay. That's going to be the important part to remember about these single term functions. Okay. Is the end behavior. So now what we're going to do is we're going to jump over to section 11.2 and we're going to talk about polynomial functions. Now this picks up actually at the very bottom of page 443, but it's just the very basic definition at the very bottom, and then it picks up on the next pages after that. So let's take a look at this. So we're talking about now 11.2, and we're going to talk about polynomial functions. Polynomial functions. Okay, so you guys might remember most of this stuff because I know we did a pretty good chunk of time in Algebra 2 on polynomial functions. But let's just take a look here. So really what we want to do is let's get down to the basics of this, okay? So let's talk about what a polynomial function is. So a polynomial function is a sum of power functions. With non-zero integer positive a sum of power functions with non-zero positive integer exponents. You know what? I messed that up. Not non-zero. Okay. Let's take that out. Let's restart with our definition of a polynomial function. A polynomial function is a sum of power functions with exponents. Okay. Let's go back here. Okay. A sum of power functions with exponents. This is what I'm trying to say here. That are greater than or equal to 0 and whole numbers. Okay, that kind of worked. So positive integer values and also 0 because, as we're going to see, a constant term has an exponent of 0. So let's take a look at the book. The general form for the family of polynomial functions. The general form is this whole string, right? It's just a sum of power functions. So when they write this as the general form, a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus so on and so forth, plus a sub 1x plus a sub 0. Okay, so what this means is that this is just a coefficient here. Okay, oops. Okay, interesting. So this is just a coefficient. This is just a coefficient. That is just a coefficient. This is technically just a coefficient. It's a constant term. Okay? So these are all just, if you notice, if you look at these separately, they're all just power functions with the three parts: the coefficient, the x, and the exponent. Right? So these are the exponents. Exponents. What's the exponent over here? The exponent's 1. Okay? And what I was talking about here is this is just a coefficient with x to the 0. Okay? So that's the general official formula or form of a polynomial function. What does this mean? Why does that change? Sorry. Still learning this stuff here. Okay. I think I got that set. Let's see. Okay. Fine. So a polynomial function, here's an example of a polynomial function. F of x equals 3x to the 7 plus 8x to the 4 minus 7x squared plus 2. There's a polynomial function, okay? So to check, really you have to make sure that all of the exponents are positive whole numbers. That was a lot easier than what I just stumbled through, okay? So positive whole number exponents. And don't worry about the constant, okay? There can be a constant. Anything else would not be a polynomial function. So again, thinking back to like exponential functions, not a polynomial because the x is in the exponent. It's not a sum of power functions. So each individual term here, right? Each individual term is a power function with p greater than or equal to 0. P being the exponent, remember. Okay? So what we want to do is we want to talk about these things, which you may remember from Algebra 2. Degree, leading term, leading coefficient, that type of stuff, right? Standard form. So each power function in this sum is called a term. I've talked about that. Constants are the coefficients. Constant term is that last value with no variable. And the leading term is the term with the largest exponent value. And the leading coefficient is the coefficient attached to that variable with the largest exponent value. Okay? So let's take a look. Let's take a look at example 2 here in the book. So which of the following functions are polynomials? For each polynomial, state the degree, the leading coefficient, and the constant term. Okay, let's do that. I don't know why that does that. Okay, example. F of x equals 3x to the 5 plus 4x cubed plus 2x to the negative 1. Is this a polynomial function? No. Why not? Polynomial, that's an O. Because of the negative exponent. Okay? G of x equals x squared plus square root 2 x to the 3 plus 1. Is this a polynomial? Well, in this case, remember we're checking exponents. Exponent here is 2, 3, and we have our constant term. So this one is polynomial. Yes, polynomial. And so what is the degree? What is the highest exponent? This is a degree 3. It's the leading coefficient. The leading coefficient is square root 2. Remember, that's just a number. And what's the constant term? The constant, spelled that wrong. Constant is 1. Okay, next one, h of x equals 2 times x plus 5 times x minus 1 squared. Is this a polynomial? Well, this is not written in standard form. This is written in factored form, which is going to be something we're going to be doing a lot of, and it can be helpful for a lot of things. This is a polynomial function. If you look again, right, we would only have positive exponents when we distribute all this out, and it'd still be whole numbers. So yes, it's polynomial. Okay, so how do we determine the degree? Well, I don't have to multiply all of this stuff out, okay, to find the degree. What I can do is I know that this is going to give me an x squared, and then I'm going to be multiplying by this x again. That's going to lead me to the highest exponent, right? And so this is a degree 3 because there's like two of them here, and then there's one of them in there, right? So it's a degree 3. What's the leading coefficient? Well, again, when I multiply this out, there's no coefficient on this x currently. There's no coefficient on this x currently. So when I multiply it all out to get x cubed, the last thing I would do is I'd multiply it by that 2, and so that would be my leading coefficient. Okay? Now, how about the constant term? So the constant term is going to come from all the constant terms being multiplied together. So I got the -1, and I'm going to be squaring it, right? Because I'm doing x minus 1 times x minus 1. And on that last distribution, I get -1 times -1, which is +1. Then I'm going to be multiplying it by this 5, so that's 5. And then we'll be multiplying it by the 2, so that's 10. So I have a constant term of 10. Okay? So, there's example 2. I think I might actually take this time to, let's just review, let's actually go over how to expand this. Let's write this in standard form, okay? So we have 2 times, oh, that keeps doing that, 2 times x plus 5 times x minus 1 squared. Let's go ahead and expand this. So I'm going to write it as x minus 1 times x minus 1. And now this is just multiplication. So just start multiplying two things together and then multiply everything else after that. So I'll square this here, just kind of go in order. So x squared minus x minus 1x and plus 1. Right, I just double distributed x minus 1 times x minus 1. I can combine those like terms. X squared minus 2x plus 1. Long way. Okay, now I'm going to distribute the x plus 5 in. And now this is where we just got to make sure we keep track of everything. First thing is I'm going to multiply the x into all three of these terms. So that would give me x cubed minus 2x squared plus 1x. Okay, that came from taking this x, distributing it over that trinomial. Now I have to take the 5 and distribute it over the trinomial again as well. So now I get plus 5x squared minus 10x and plus 5. Now let's combine like terms. I only have 1x cubed. I have a negative 2x squared and a plus 5x squared. And then I have a 1x minus 10x and my constant term of 5. Last step, distribute the 2. And there we go. Okay, there's standard form. So that's just a little review on how to distribute these factored form polynomials into their standard form. All right. Now what we're going to talk about is we're going to talk about the long-run behavior of these polynomial functions. So remember we talked about the long-run behavior of the power functions. The polynomial functions are going to actually be very, very similar, okay? So the long run or end behavior of polynomial functions are determined by the leading term. the leading term, okay? They are the same as the power functions. So that's the reason why we did that in the power functions, right? Because if we have a polynomial function and all the little terms, all the little individual terms are if we have a polynomial function and all the individual little terms are power functions, then if we only look at the first leading term, then it's just one power function, and we do the same thing we just did with power functions, okay? So let's take a look at an example. Yeah, let's take a look at this one. Example 4. So here is a polynomial function. We have q of x equals 3x to the 6 minus 2x to the 5 plus 4x squared minus 1. And we want to know the end behavior of this. Well, what's the leading term? The leading term is 3x to the 6. It's the largest exponent, it's the leading term. Okay, so it's a positive coefficient, so there's no reflection, and it's an even exponent, so I'm going to sketch that out. It's going to look like that in the long run, right? Even. Looks like x squared in the long run. So now we can identify the end behavior. So I could say that the limit as x approaches infinity of, I'm not going to write all that out, I'm just going to say q of x, but it's of the whole function, of this whole polynomial, the limit as x approaches infinity is infinity. And the limit as x approaches negative infinity of q of x, as we go to the left, that also goes to infinity. Okay? So the end behavior of polynomial functions, almost exactly like the end behavior of power functions, we just have to look at the leading term. Because in the long run, x to the 6 takes over all other variables. X to the 5 is not as powerful as x to the 6. Okay? So that's all there is to it. We got through 11.1 and 11.2. We got some problems posted for section 11.2, and yeah, those problems pick up on page 448, and I will see you guys next time. Don't forget to let me know if you have questions and if you want to go over anything. Okay? All right, see you later.